speaker is Mr. Chinmay Naik. He is from AMNS, that is Arsenal Mittal Steel, and he has been working there from past 6 years. His area is learning and development with strong focus on the manufacturing and engineering talent development. He has been involved in designing and delivering structured training programs for trainees, young engineers, and first-time learners. Largely, his work revolves around work-integrated learning, proficiency-based skill development, and translating technical knowledge into shop floor-ready capabilities across mechanical, electrical, metallurgical domain. Sir, collaborate closely with academic institutions also to bridge the gap between classroom learning and industrial expectations. Sir has completed his BE in 2009 and Masters in 2012. He is having both academic and industrial experience. Presently, he is working with AMNS, as I said. So, over to you, sir.
Am I audible?
Yes, yes.
Shall we begin or just we are waiting for someone?
Yes, sir, you may start.
Okay, sir. Okay,
You're
first of
audible.
all, thank you very much for this opportunity for this Atal training program hosted by SN Patel Institute of Technology. Thank you, Dr. Chirag Naik, Dr. Ravi Sherpara. So, as I understand that the audience are from the various colleges, professors, assistant professors of the various colleges. So, it is quite great pleasure to join this dignitaries of the fell state as I belong to industries. But again, I'll just focus on the technical aspects more or application aspect. So I hope you may relate this to while delivering to your students, while preparing your students for their future. So the focus will be more on the automation side, Industry 4.0, IIoT, and aspect of artificial intelligence and the application part. Okay, so in next 1.5 hours, I try to cover all these aspects. So let us begin with I think I'm the organizer. Okay, fine. So it will be difficult to communicate with all. So in during our or if in meantime you can respond in chat box if I ask few questions, because it will be useful to make this like I'll be interested to make this session more engaging. Okay, so that is one aspect. So before we begin, let me just share my PPT and. Oh, wait, just give me a couple of minutes. Fine. Okay, is it visible? Okay, fine. So we'll be talking about artificial automation technologies. First of all, PLC SCADA overview, then the communication, then we'll move on to Industry 4.0 IoT and artificial intelligence. And most importantly, in today's world, the buzzword is digital twin. So use cases of AI in industry. So combination of both this thing, AI and the SCADA part, we come with we have a digital twin. So before we begin, can you have some interactions that what is automation, as I believe? If somebody can answer, if somebody can respond to this, what is automation? Like everywhere in all our daily life, we are having technologies by some or other ways. So what is automation? If I ask you, then most related to the like it is more related to industrial automation if you focus more. Then this automation refers to use of technology or a control system or a machinery to perform manufacturing, production or industrial processes, that is with minimal human intervention. So the main here idea is minimum human interaction. So how we are doing it, like mean for minimum human interaction, but with it integrates both like mechanical, electrical, or a computer-based system, and which will enhance your efficiency, precision, or productivity. So when it comes to an industrial automation, the focus is more on the efficiency and the productivity. So here the thumb rule is, if I am like I am investing in some technologies, then it should give me a return as soon as possible. So with that, in today's world, these industries are evolving, and they are very rapidly evolving with the automation. So with it, like the conventional ways are there still, that people have adopted, and it is well known that the simple automation, that is PLC and SCADA, we are all aware. But the, it has gone beyond that. In the market, like the buzzword which is all of you are talking about, that is artificial intelligence, and it has created a disruption in all the field, and this industrial automation is also not far behind. So uh, that is this is what the basic automation, we are limiting human intervention. So as many as the use of technology will result into an enhanced production and precision. It may be any industries. So this is one aspect of automation. Of course, increase productivity, accuracy. You can increase your reduce complexity in wiring or anything, like as far as the hardware is considered, then mitigate the effect of labor shortage, improve product quality, accomplish the work where human being is not accessible, and in of course competition in the market. So we are all aware about the or use of automation. So as of now, let's say we are living in this era. So let us just go back to the revolution which has taken place. Let us try to understand. Now, all of you are hearing about Industry 4.0, 4.0, but let us quickly glance through the what was the previous revolution, and today where we are, how we have reached here from the past over of like 100 years or 150 years from where we started, and today where we are. So in the era of globalization, when we started with this, before 100 years, there was a first revolution which has taken place. So in this slide, I have represented a journey from industry 1.0 to today, like in the era of 5.0. Still, we are in between somewhere industry 4.0 and 5.0. So looking at this slide, can anyone have can anyone respond that where we are living, like are we really at industry 4.0 or a 5.0, or like we have accomplished this 5.0? So can anyone write in a chat box, or can I have a responses, so that the session can be more engaging? Think okay. 4.4, somebody has written 4.4. Okay. 4.0 little. Okay. 4.0. So we are into industry 4.0, and in some of the sectors have adopted 5.0 as well. So what was that industry? What was that before 100 years or more than 100 years? That was the first revolution which has taken place, and it is invention of like steam power, or use of machinery, water power, steam power, and the first industry which used this industry 1.0, which was the textile industry. The first experiment which were happened in form of industrialization was a textile industry. So this very well, like we were knowing about, we have an idea in literature the power of steam, and at the time at the same time steam power was like um, rudimentally driving small industries, small handicraft industries, and this hand or weaving looms. there the first use of steam power was there, and ultimately the people adopted in those era, and the revolution started in late, even to be precise, in late 18th century. So after 1875, this particular industrialization started, and soon after that, like people were in dire need, people were wanting more, and in this process, of course, the term called mass production came in. So this mass production was a concept that was realized in early 19th century. And if in during those time, if you wanted to achieve this mass production, then of course it has to be that some, like some other mechanism by which you can achieve. So in during this era in industry 2.0, it was an electricity which was commercially used. So main aspect is whichever technology we have, the commercial use is very, very important. Whatever we have in research, whatever we have in literature, it is there. But unless and until from industry perspective, unless and until it is realized into a commercial solution, unless and until it is the it is the problem, or it is the daily life, then that research still has to prove its validity. So we were having we were knowing about electricity. There were paper, there were Fleming's left-hand rule, Fleming left-hand rule, Land's rule, everything were there. But unless and until that electricity produced in a power plant, transmitted to some plant use it for their commercial activity, that product from that plant is sold in the market and revenue is generated, in which help into more such kind of investment, until and unless that research is of, like, still it is in a literature phase. So in early 19th century, this electricity was generated. It was commercially given to some plant, and to be precise, some like here, it was the first experiment was made in Germany, and it was an era of a world war, second world war. Everyone is aware about the Hitler and his desires to conquer the world. So he exploited, or he used this particular technological aspect, and like he conquered the world and fought with the world. So to produce weapons, artilleries, in terms of mass production, he used electricity. So we were knowing concept of generator, we were knowing concept of motor. So on a conveyor belt, you can have a mass production. So that the first this commercial use or concept of mass production was used, and after that we know that Germany is still ahead in automobile. So soon after, it was used in automobile industry. So you can see, you can imagine those black and white videos where that one conveyor belt passes through, and some wheels and other body parts are sequentially put on the on a belt, and finally the product comes out. So that was an era of industry 2.0. It continued, and world adopted this as an, like, as a growth, and this continued, and finally this industry 3.0 came in around 1967, around after 1960. So this a very important era of industry 3.0, and it changed the whole game, and actual disruption started during this era. It was an era of computer. It was an era of digital electronics. So digital electronics resulted into a computer. And finally, this computer was in, when it, if we talk about the industrial automation, then this computer is resulted into industrial computer, and a first PLC was conceptualized. So programmable logic controller, that we are aware about this, and it was the first PLC was invented in 1967, a company called Modicon. So they invented this, and they used this first PLC in some fertilizer plant. So after 1960, as the digital electronics and computers were commercially used for industrial application, same one industrial computer was invented. So ultimately, industrial computer is nothing but a programmable logic controller. And after that, the subsequent technology of PLC, SCADA, and they grew. The whole industry, all the segment of fertilizer or pharma sector or this mining industries, they adopted this technology, even energy sector. So in all slowly all sector of industries adopted this, and they used it for their own advantage. Like the benefits were quite visible in terms of revenue, efficiency, and productivity. So everyone were happy to adopt this. So this continued, and slowly it built up the acceptance. And finally this industry 4.0 came in. So after 2010, it was the actual era is of industry 4.0, if I say. Then it started after 2010. So it is an era of an internet. It is an era of a cyber physical system. It is an era of a networking, to be precise. So here, earlier we had a PLC that was functioning, that was controlling your plant. Now that PLC has got its own IP address. So that IP address is ultimately gave it to a connectivity. Each IP address, today we are having intelligent electronic devices, starting with this numerical relays to your this PLCs and other high-end devices. Those are all intelligent electronic devices. So each intelligent electronic devices, they have got now their own IP addresses. So ultimately, that is it is in this era of Industry 4.0 where this networking and Internet of Things came in. So Industry 4.0 is about Internet of Things, application of Internet in our daily life. To be precise, in industry, it is Industrial Internet of Things. So we call it as IIoT. In this era, I cannot imagine my system independently monitored and controlled. All this are controlled from a central observer, or simple by one click. Let's say if in terms of in terms of substation we are talking about earlier. So by sitting here, I can control any breaker, any relay of the world of any substation. Like if provided, I should have a right to penetrate in that network ethically. So sitting here, I can trip any breaker of any network. So that's the power of Industry 4.0 or Industrial Internet of Things. Sitting here by one click, if I can stop production from any plant, that is a power of Industry 4.0. That's how your total automation is converted, and it has changed all game. So the actual digitalization started after this, and it is still progressing. It is increment the benefit, and the industries are leveraging the benefit of this exponentially. And these OEMs, like those who are technology providers, they are coming with a newest to new solutions in this era. Okay. So slowly, when this robotics and AI came in, then finally the era of Industry 5.0 will come in. So around after 2020, we have human or cyber physical system. Human cyber physical system. So we have manufacturing, engineering, and technology. This three aspects. These three aspects basically converted into one area, that is a cyber physical system. So, and here again digital twin comes in, where
Just wait for a minute. We are fixing it up.
Am I audible now?
Yes, sir.
Okay, apologies that there was a network issue, I think. Okay, just give me- sorry for the interruption. Now is it visible and audible? I hope.
Yeah, yes, sir.
Okay. Yes. So we were talking about industrial revolution. So the example which I was giving is you're using mobile phone today, and in mobile phone, like if you compare it with like before 20 years, and you compare those mobile phone with now, they are a lot more smarter and lot more capable. So same way before 20 years, there were PLCs. Before 10 years, there were PLC. And the main function of any PLC is to start and stop. So same way, in today's world, with the use of IIoT, smart sensors and everything, still the basic function of a PLC is to start to stop. But today, the same PLC is lot more smarter, or lot more, the capability is a very advanced level. The physical, is it not visible? PPT is not visible. Okay, so somebody wrote in a chat box, so that's why. Okay, so what I mean to say that when your PLC is there, today's PLC is lot more smarter, but the basic function will remain same, is to start or stop, to start any process, to stop any process, to start any motor or any controller. So
Hello, your PPT is not visible. Oh, okay, okay, okay. Now, okay,
okay,
okay, okay.
okay, now okay.
Continues, please continue.
Sorry for this interruption.
Okay, okay.
Now, let us, after going through this fifth revolution, still it is yet to come 100%, but it will come soon. So the idea is your automation devices will be more compact, the design will be more compact, but at the same time, the capability will be lot more. Okay. And it will again enhance the overall productivity, and it will enhance the efficiency. So basic aspect of industrial automation, it is like your uh, it refers to industrial process manufacturing, assembly, and packaging automatically. So we have in overall as a package, there are three aspects. One is the field devices, the second is the hardware, and third one is the software. So hardware and software both control the field. So in the field, you have sensors, actuators, valves. Your hardware is your PLC, HMI, DCS, and the drives, all motor drives. Then all these PLCs and HMI, they are controlled by a software. Same way, they are programmed on a technological software, whether it is Siemens, ABB, or Schneider, whichever PLC is there, they are programmed that way. Then you have a software. So your SCADA, when you term a SCADA and a PLC, PLC is generally a hardware. SCADA is your hardware. Sorry, software. So PPT is visible. Okay. So SCADA is basically your software part, and PLC is hardware part. But to program the PLC, you need to have a knowledge of a software. So if you have a Siemens PLC, then there's a different programming system. If you have a Schneider PLC, then different programming software. Same way as for the OEMs, which are like original equipment manufacturer, it depends on them, and it varies from the product to product. It varies from the development to develop. So here both the aspect, hardware as well as software, needs to be known from the industrial automation point of view for to provide any automation solutions. Okay, so to understand more or in this automation aspect, so this is pyramid. So this pyramid is generally given by the International Society of Automation, which is your ISA. So in this pyramid, there are different levels. So how the actual automation takes place, and where your artificial intelligence and data science come in, that we'll discuss in this aspect. And so you can see here you have sensors, actuators, and we call it as a L0 level. So it is your field level. So they are the actually foot soldiers. They are working on the shop floor. Above it, there is a control level. So in this control level, your PLC and mostly DCS. So PLC and DCS stays at the control level. So L0 level, L1 level. Above it, you have a supervisory level, that is supervision level, SCADA. So SCADA is at, you can say L2. So L, if we start from L0, L1 and L2. So L0, L1 and L2, they are part of this field level, control level, and super level, and they basically control the whole process. They make the process automated. Above it, the management level, and we call it a manufacturing execution system. So from industry perspective, whether you take it an automobile or a pharma or for that case, a steel plant. So this MES plays a very, very important role. So in today's world, if you want to do something, or if you want to have a project or a consultancy, then this aspect in industry is attracted by, like, it is of area of interest, because at this level you need MES. At MES level you need a domain expertise as well as the technological advanced, know-how of the technological advancement. So at this L0, L1, L2, and L3 is like the link between the top level and the bottom level. So at the top, you have a ERP, that is Enterprise Resource Programming, we are all aware. So it is at the enterprise level, the management level. So most of the industries today uses a SAP. So SAP is like a management or automatic process tools, or this system plays at the top level where your sales, marketing, even inventory control, your material management to production planning, everything is plays at the top. So management decide what to do and when to do. Now they give, and from the top level, the instruction come to, or the business requirement or business planning comes to the downwards, and all these downward level are integrated such a way that the productivity is enhanced. Okay, so here MES is like they schedule everything, they control everything. So when on which process will take place, or which SCADA software will get a signal for, let's say there are a shift or operation going on shift. So to do a certain activity in this shift, this kind of activity will be done. We have this inventory, we have this production plan, and based on that, the process will be executed. So manufacturing execution system is a real world challenge to convert into 100% digital factory. So the digitalization is started in this at this particular level. So SCADA and PLC are at its place. But let's say if you want to have a autonomous maintenance, if you want to have a predictive mechanism, then both the thing can be included at SCADA and MES. How that we'll see in later on slides. But the MES technology is still evolving, and it goes hand in hand with the management and the shop floor level. So that's why it is very, very important. So let's say if an 8 hour shift planning in a shift, all three aspects of the operation, performance, and a product quality is covered at this level. So it, like, as of now, let's say if you don't have any exposure of industry, it is difficult to understand. But imagine that at this level, you are getting instruction from the top level about the production plan, about the revenue. At the same time, you are cascading this information to the bottom level. So at bottom level is an execution part. They will run the plant. They will get the production done. So that's how the whole automation is achieved. So this pyramid is basically gives you the holistic approach how industrial automation works. Okay, so I hope this thing is clear to you. Okay, so in between, if you have any question, you can write in chat box also. Okay, so now, next, let's move on to the next slide. This is basically just give you brief idea. We'll not talk in much detail, but whatever I have discussed, this is in a framework. This called as SCADA's framework. So at the field level, at the PLC, and at the top, you have a SCADA software. They are controlling the plant. So that's how simple automation is achieved in any industries. Okay. So, and this is some simple SCADA screen. So you can recall like whatever you used to teach to your student. So this is your basically SCADA PLC combination with the field level. So this is how you achieve the your automation. So here, next is the auto open system interaction or this OSI model for communication. Now, the second very important part is how this devices communicates with the PLC and PLC communicates with the SCADA system. Okay. So communication, and to be precise, industrial communication is very, very important aspect to achieve the 100% automation. So here, to achieve automation or to get the data, even to apply any AI machine learning algorithm, you need data. So these data are communicated via different protocol. So if there is a substation is there, then substation communication is there, then IEC 61850 protocol we are aware. But when it comes to industrial automation, the communication protocol is different. So you cannot have the same methodology for all sort of communication. So here there are like a Profibus or a Modbus communication. It is widely used. Now slowly we have moved from this Profibus or a Modbus to a Profinet and Modbus. Okay, Profinet or intranet based communication. So all these devices have a communication this way. So they are different level where a physical layer, data link layer, network layer, transport layer, or a session layer, presentation layer, and application. So here you can see the screen. Say, let us, this is what a SCADA screen is. This is actually an application which is came out of your process. So this application is made at the last layer. But to get this, let's say this is some tank which is getting filled up. So if this tank response or the level which is indicated here, it communicates from the shop floor. So the data passes through a various layer, that is your transport layer, a presentation layer, or data link. Or in a way, in short, if I give you an example, or by this, like let's say a level, temperature, or a pressure data from the shop floor, second by second, updated in the database, and this database is converted into a graphics in form of a SCADA screen. So SCADA screen is having a graphics, SCADA screen having some trends. So trends are in terms of your level, temperature. SCADA screens give you the idea about the alarms. SCADA screen give you the numerical value of all these parameters. So whether it is a trend or a trend or a alarm, directly it is indicated on a screen. Okay, and that's how it helps a operator to take a real-time decision. So in this, let's say trend is in no audio. Am I audible?
Yes, sir. Yes, sir. Please go on.
Somebody is
Uh,
okay. So
yeah.
okay.
Okay.
Somebody wrote no audio. That's why.
No, 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 no. Please continue.
Okay. So trend is like your database. So from database here, a graph is reproduced and it gives you the real-time information. So that's how your normal SCADA screen works. We are all aware. This is just I'm giving you what is important to go further. Okay. So this industrial communication, we have Profinet, Modbus, Ethernet, or Ethernet. But in today's time, the basic behind is a master-slave communication. So master-slave communication is a science behind Modbus and Profibus. So with all your PLC to server and to from the server to database. The communication takes place based on this Profibus, Profinet, or Modbus protocol. Okay, so these are basically different protocol or the highlighted protocols. They are actually used in industries. And nowadays, as I told you, it's an era of networking. So all these PLCs and intelligent electronic devices, they have got an IP address. So through IP address, you can communicate wherever, whatever. Okay. So of course, but the devices which are there, they will not understand your normal language. So Profinet based communication protocol or the data transmission, digital data transmission is very well understood by the processor inside the PLC. So whether it is PLC, SCADA, DCS, or whichever automation device is there, even to communicate with the robots, there also you need to have a communication based on this protocol. So to realize or to have an efficient automation technology, the heart is the communication. How fast you can communicate data from field devices. Likewise, your thermocouple, RTD, or a level transmitter to PLC, from PLC to SCADA software and a database server. So once a minute by minute, let's say pressure data or a level data or even motor current data, second by second data is available, then the algorithm which are brought behind to take any AI based or machine learning based decision, then this real time data will be helpful to take a real time decision. So here, as the technology advancement has taken place, the data communication, the speed of the data communication is also very important to use any AI or a machine learning tool to have in this environment. Okay. So the first priority is make your communication fast and efficient. Then and only you can take your autonomous decision. Otherwise that uh, uh, somebody is ask a questions will come back. A node is basically your one, let's say one IP address is there. So in that communication port we call it. Okay. So we'll come on part, whatever question you have, we'll discuss this part also. Okay. So this is basic simple technique of master slave. So in this technique, master devices issues commands to one or more slaves and slave respond. The slave is like master is like master receives data from this data, let's say sensors or a or a temperature transmission or a motor status. Then this master generates a signal and based on that it receives the output. So every 40 millisecond, PLC's processor first check for an altered input in local rec. And then it sends a query to first external rec to see if any input have changed or a hardware failure had occurred. So that's how like a master slave communication takes place. So this is kind of, let's say here, so this is your PLC and this is your master device. It communicates with all these slaves. So you have some valves, some motors, some control valve, and unless and until it will generate one schedule, it will generate one signal, and it will check the all the status is change. Check the status. Once the status is changed, it will respond. Okay. Same way your cyclic communication and this for again these are this picture is of your PLC, actual PLC, a Siemens PLC S7300 PLC. So all this in right side the pointer where are these are the IOs. So in one PLC you have hardware. In the hardware you have processor, then you have communications, and with that communication these are all inputs and output devices. So PLC is like receives input from a sensors, some program is written. We are all aware how the PLC works, and based on that program, it generates output. So this the where my pointer is, these are all inputs and outputs. With this, it receives the sensors inputs and generate output. So the communication is either Modbus or Profibus. So we have RS485 cables are there, and generally with the PLC, if you have seen this, then there are the purple and a green cable. So these two cables here, the port is also there. So generally RS485 cable is used in SC7300 PLC. Now the technology is advanced, so we are having Ethernet based communication also. So this is simple example. RS485 cable here, this is your separate out IO devices. We call it as inputs and outputs. So PLC, again, I'm repeating, PLC receives signal from inputs and outputs. Okay, so your input may be the status, or input may be a thermocouple reading, input may be your a level reading. And based on that, let's say if I want to fill a tank, then tank is 100% filled. I have to stop the valve, or I have to stop the motor. Then the same way the output is given from this module. So IO module and the PLC, that's how the communication takes place. So next is the very important protocol. This is TCP/IP. So as I told you, every PLC, the modern PLC has got is IP address, and this communication can be done with this TCP/IP protocol. This is transmission control protocol, or we call it as an internet protocol. And they are used together as internet and Ethernet network in commercial or organization. So this is basically, it gives you the idea how this actual intranet works, and based on that protocol it works. So here you have another sort of communication, that is Profinet. So here actually the Ethernet based communication takes place. So this switch you might have seen in some data server. So same sort of switch is used in industrial environment also. So these switches are helpful to communicate with PLC, DCS, and or other smart devices, or it can have a communication from relays also. So it's combination of all devices, they are connected with this switch, or we call it as an Ethernet switch. So normally this Ethernet switch is, let's say it's it for IT networking, but this is also for your industrial data networking, and it is called as operational technology. So when it comes to an industry, there are two terms. One is the IT and the other is OT. So operational technology data, a very, very important data. Those data are communicated separately, and the IT data. So proper intake, when you will be able to realize this industry 4.0 in real sense. So in real sense, when you will be able to converge both IT and OT data all together, then and only you can realize industry 4.0, 5.0. But still industry is so conservative. There are risks that we'll discuss why it cannot be converged 100%. So IT and OT data, you keep this word in mind. We'll discuss later on this IT and OT. Okay, operational technology data and IT data. So many times the combination of both this Profibus and Profinet, both are there in a PLC, and the communication can take place. So here MPI, this is multi-port uh, interconnection. This, say if you want to connect a laptop, you have to dump a program, you have to use this MPI port. So Profibus, Profinet, all this like 8 bus addressing, we are aware that how this digital data or binary data are converted and transmitted in this. So this how the like simple number system, if you want to recall, a same number system is applied here also, and 8-bit data is transmitted between field devices to IOs and IOs to PLCs. Okay. Now, let us quickly move on to this. Uh, Up till now, whatever we have discussed about PLC, SCADA is your software. In SCADA, you have two things. One is your engineering station, the other is the operating station. SCADA is your 100% software. It is a representation of a real-time environment in terms of graphics, in terms of trends, in terms of alarms. And PLC is basically with that the automation takes place, programs are written inside is it takes continuous input from the field. Based on the input, some logic is written, and from that logic it generates command, it generates output to on the field. So PLC and SCADA all combining, it gives you the automation solution. But it is technology that, but it is continuously evolving. So the one aspect is this industry 4.0. So without, let's say, if you want to achieve 100% automation without PLC SCADA, you cannot achieve. If you want to have industry 4.0, then there are a lot of capability of the same automation system. So how we can do, or what is industry 4.0 in actual? So it is like a name for the current trend of automation and data exchange in manufacturing technology, including cyber physical system, Internet of Things, cloud, and cognitive computing, creating these smart factories. So this, let's say cloud computing, yeah, everyone has yet cloud computing and Internet of Things. But when it applies to the manufacturing environment, and it is very crucial to have this technology in actual manufacturing setup, because at times we at times the industries is very conservative. So the main aspect is of investment. So how we can have, like, today is industry 4.0, tomorrow is industry 5.0, then how can we have this kind of capex every year? So it is many times it is difficult to adopt those technology as soon as possible. But there are upgradation. There is a chance of upgradation everywhere. So once the industry sees a ROI, then of course they adapt those solutions. And at the same time, the solution provider, all these original equipment manufacturer. Let's say if I give you example of any manufacturing plant, then plant, let's steel plant is there. One plant is there. But to provide solution, there are vendors. So if a Siemens or a ABB or a Schneider giving you the solution, then the industry accept. So one is this manufacturing industry, which is actually in the business. And to support the business, there are solution provider. There are technology provider. There are OEMs, which are like original equipment manufacturer. So they give solution related to, let's say, Industry 4.0 or IIoT. So they give the solution which make their life easy. So once the industry find, once the business find a better ROI, then readily they will accept. So Industry 4.0 is that thing only. If like we were having PLC, we are having SCADA system, why should we go for this? Because there are, like, there are advantages. You can have a shorter downtime. You can have a, like, near zero unplanned breakdown. You can have a better visibility, a central command. Then you will have to adopt this industry 4.0. So many times it is very difficult to convince those conservative mindset, but if you want to progress, then we have to adopt the technology. So that's how the industry progress. Okay. So it is basically a use of both this, like data exchange is also there, but in manufacturing environment, including cyber physical system. So what is cyber physical system? Cyber physical system is like whatever physical system you are seeing, let's say motor or or a compressor or a valve, a same motor or a valve is appeared on your computer screen. Same way it takes the decision, okay, automatically. So everything which you see on a shop floor, it is on a cyber world. So that is what the cyber physical system. And the main aspect of industry 4.0 is a cognitive computing. So what is cognitive computing? What I will do with this millions of data? Let's say every minute my temperature is changing. Every minute my level is changing. So itself that technology have that computing mechanism real time, or a cognitive computing that we call it. So it like there the capability of automation decision taking. It is called as a computing or a cognitive computing. Okay, whether this level data is acceptable or not, whether temperature is under limit or not. So real time decisions can be taken, or you can predict the health of your equipment. So this capability comes with cognitive computing. Now we have seen about condition monitoring, real-time condition monitoring of a motor or a transformer, or there are many precious equipments are there. So if those equipments fail for a minute, then it will result into heavy loss. So to prevent this, real-time cognitive computing should have with this, it comes with this technology. Okay, so it should have. So ultimately, it will create your smart factories. So smart factory is not with just one communication tool. Smart factories is communication, fast data transfer, and fast decision taking. And in backend, there are multiple algorithms that are running behind. So this is basically about, this is an explanation about what is industry 4.0. And this is actually applies in now, like all the industries are adopting the solutions based on industry 4.0. So to be more on this is like it is more automation than the third industrial revolution. It bridging the physical and digital through a cyber physical system enabled by industrial IoT. A shift from central industrial control room to one where smart product define the production step, closed loop data models and control system. So there are, like I have received a temperature data, but whether with that temperature data I can predict the health of my furnace. I have received the current data. With that current data, I can predict the health of my bearing. I can predict the total health of your motor. So this closed loop actions are enabled with Industry 4.0. So by embracing this, companies can modernize their remote workplace and collaborative capability. So in plant, generally there are different departments, and there are different areas where the systems are employed. Okay. So by just one click, you can have all the information, or you can like the other department also may be aware about this. So organization can conduct predictive monitoring and diagnostic of operations and assets. Very important. Okay, predictive monitoring. And this process automation and advanced analytics can improve your process decision making, and the supply chain becomes more resilient and connected. So the idea is to prevent unplanned breakdown. The idea is to have 100% reliability of your electrical, mechanical, or whichever process equipment out there. Okay. So with this, you can, like with Industry 4.0, you make them efficient as well as the precise working. Okay. Then what is IIoT, or Internet of Things? It describes as a network of physical objects that are embedded with sensors, softwares, and other technologies for the purpose of connecting and exchanging the data with other devices and system over the internet. So here, like only hardware will not be sufficient. At the same time, you need you need software capability. So to run any hardware, you need a software which communicates or which understands those languages. Okay. So you require both these things. So industrial internet basically provides a way to get better visibility and insight into a company's operation and assets through integration of your machine sensor, middleware, software, and backend by a cloud computing and storage system. So as I told you, middleware is like it connects two system. Okay. So you have advanced sensors. Sensors have a communication capability. So up till now, you have seen that thermocouple will convert say analog data to digital data. It will be displayed on 7 segment. No, now the advanced sensors are there. They have the communication capability. Sensor senses the data, transmit the data on the cloud. On the cloud, you have some algorithms are written, compare the real-time data and predict the health. Okay, so the sensors have more capabilities. So this is what your industrial internet is, and this just gives you idea about the plant Ethernet network. Of course, you may not be so much interested, but this is how like we have PLC. With every PLC, there is a remote local control as well as the remote control, and it is connected with the different servers. So like you may be amazed that in a control room, server is also very, very important. So uh, each and every plant network has its own intranet network where the operational data communicates. Let's say if you have a college and in college you have servers, in that mostly a data related to IT data, your email data, let's say your attendance data, or the communication or information data transfer. But in a plant Ethernet network, my level, temperature, start, stop, all these signals are communicated in this network. Okay. So this is basically example of the pass network. So here, the next aspect is quickly I'll take it through the OPC. So basically, what is OPC? OPC is like your uh, this in server communication. That is OPC. Sort of whatever data are there, those data are stored on some server, and these servers are known as OPC servers. So IoT brings together a broad range of technology that have not traditionally connected via normal IP-based network, but when it comes to a reach, you have to be like it should be understood by everyone. So horizontal communication or a machine to machine connectivity is there. Now the same machine if wants to transfer the data on the cloud, then you need in between some server. So OPC is basically a unified architecture, and like if you simple write an OPC server on internet, that it will give you the how the industrial data are communicated with this. It is how helpful is it. So nowadays the system from a local server to moving to this OPC network. So OPC is a very, very critical part. So in substation communication or this industrial data communication, OPC server plays a very, very important role nowadays. So mostly all are from electrical. So we are aware about this Indian Energy Exchange and how the trading take place. Now, all those power trading. So, to give you example of this OPC unified architecture, your ABT meters are there in all these substations. Okay, if there's an industrial substation or any Jetco substation or a power grid substation, the ABT meters communicate via OPC server of energy exchange data server. So the real-time settlement which take place, let's say if a renewable source or a thermal power plant source, you are procuring power from both this entity, and the final settlement which takes place. So here, this OPC servers are plays a very, very important role. So all those power usage data via ABT meters, it goes to OPC server. And on from that OPC server, the Indian Energy Exchange take place the data of the power consumption, and based on the unit prices, the settlement takes place every day. The contract are renewed every day. So in every aspect, or this OPC server is very, very useful. And because of this OPC, your industrial Internet of Thing is realized. Okay, and a very efficient way it is realized. So here it is. So earlier, we had seen this pyramid. If you recall again, so Internet of Things, like here at the base, you have a factory floor or shop floor where the data is transferred with Ethernet, PLC, OPC, UA, that is unified access. So from UPC here, the data goes to cloud, and the cloud, the various actions take place, and again the data communicated to this PLC. So PLC, SCADA, MBS, and ERP. In between, that is OPC or Unified Access Server data are stored. So from here, from this stage itself, you can access the data and store on the cloud. Okay. So that's how it is very important to know about OPC architecture. So before going on to this AI part in last half an hour, let us understand the operational and technology and IT, information technology. So to realize 100% artificial intelligence or a machine learning based solution in industrial environment, we need to integrate IT and OT. So IT and OT aspects, both these aspects are so important that without understanding, like, IT people cannot also do anything, or even to discriminate, like to have a to difference between, if I give you example, like IT is like all those computer IT people, they are just aware about the softwares or a .NET framework or a database or their web application. While operational technologies, they're all like our electrical and mechanical engineers, they're working on shop floor. But as we are all aware, without anyone, like whom will provide, the IT guys will develop a solution, but in that solution, if you don't have a domain knowledge, whatever, then it is of no use. Say the same IT solution I have to implement in manufacturing industry, then I must have a knowledge of that domain part. I must have knowledge of the temperature or level or a transmitter, or even this IT guys will not be able to understand whether this level is a discrete data or a analog data. Barabar. So here, to have a proper solution, we need to integrate both this thing. So operational technology will have your the main players are engineers, technicians, operator. Like then IT will have a computer science, information systems. Okay. Business priority is like, for when it comes to a business priority, for OT, it is like availability, zero downtime, safety, and asset protection. So this is related to your shop floor and a plant environment. While for an IT, it is data integrity, confidentiality, information management, and manipulation system. Okay. So to give you more example on this, a simple example is like in a plant, if I have a computer on the screen, if I am monitoring some plant process, then the same computer is able to communicate the current, voltage level, temperature, pressure, motors data, compressor data, all those data. But from the same computer, I'm not able to access my email, or I'm not able to surf on a Google or a chat GPT. So that system plays in a control room, is connected in a network, but but I will not be able to access the IT data. Okay. So that is what the difference is in very, very simple way. Computer is there, data transfer is taking place, but these data are mostly related to operational data. I cannot access my email from the same PC. Okay. So that is what the difference. It is not connected with the IT network. So I hope you understand the meaning of operational technology and information technology. So here the components are your control system, sensors, actuators, your legacy system, which are old one, and external data source. While the IT system is your ERP, CRM, then your SaaS, that is software as a service, asset management, cloud, data as a service. So both these aspects. Then your environmental condition here, it is very harsh while it is air condition. So out of all this, if I want to have a solution based on AI or a machine learning, I need to incorporate this. S- Still, like industry, still a conservative. They have still operate approach of conservativeness. The reason being, the moment I integrate IT into my OT technology, then the main threat is a cyber security. So this a security aspect is a predominant when it comes to have this kind of solution in industrial environment. So there is a threat, there is a data breach, and we are all aware about the cyber threat and its consequences. Barabar. We know about like few years back there was a cyber attack on a Ladakh grid, a power grid. You can still search on Google, you can get the more information on it. Before few years there was a cyber attack from China on a Ladakh grid, and they tripped one whole transmission line. Even few years back there were a tree cascade tripping, or there was some main line was stripped in Maharashtra from some Tata power plant to their main substation, which was feeding power to local train network, railway network. So after reports, it came to light that there were some cyber attacks. So this, if you integrate IT and OT both in an industrial environment, then there is always a threat from the external sources. It is believed by the industry people. So that's why they are still hesitant to have 100% solution from AI based or a machine learning based. I'm telling you, because still the manufacturing industry is conservative. They are not adopting this solution as quickly as like there. It is very difficult to convince people to go for such kind of solution. If it's some isolated system, if you give them database isolate, if you give them access with some other port, then it is very easy. They will readily accept, but to expose whole their system for 100% solution, it is quite difficult to convince them. The reason is simple: a cyber threat. So once you expose your data, it is very difficult. So what happens is, let's say if there is some motor and predictive mechanism is taking place. So on a cloud, the service provider will ask me that you give me your motor data on a cloud. On cloud, they will have other industries motor data. Very simple example I am giving you. So on cloud, there are multiple datas from same sort of multiple motors installed in other industries also, and data are coming on cloud, and based on that data only this algorithms gives you the result. Okay, so that's why your data are exposed in the IT network. So that's why it is difficult to integrate, but sooner it will come. There are strong firewall, there will be a strong security system at plates, and the total solution will be realized. That we are seeing in near future, we will have 100% smart factories running on a solution based on AI and ML, which will prevent unplanned breakdown. That is the biggest worry of any industry. Okay, so that aspect sooner will come. Okay, so let us quickly everyone know about what is artificial intelligence, how it is implemented. So artificial intelligence is basically a machine's ability to perform cognitive function as a humans do, such as uh, perceiving, learning, reasoning, and solving problems. So here the main aspect is to solve problems. Okay. So it helps to reduce amount of time needed to perform specific tasks. It will make making it easier for humans to interact with the machine. Very basic thing I am explaining from the aspect of manufacturing industries, facilitating human computer interaction in a way that it is more natural and efficient, improve the accuracy and speed. So helping people learn new information more quickly, enhancing communication between humans and machines. So earlier, if like the time taken by that temperature, like here, in a steel industry, if I give you example, a very important factor is the temperature. When the steel melts at certain temperature, there's an indication which I like. If I want to desired chemistry of a steel, I want to achieve a low carbon product, then I need to get the temperature of 1500 degrees Celsius. So the moment I get 1500 degrees Celsius, there are different interlocks and quick decisions are taken. So if it is made autonomous, it is very helpful. Okay. So, subfield of artificial intelligence, you might be knowing, you might have used in your literature or in your research, but nowadays, slowly, it is implemented in industrial solutions. So, these are machine learning. Machine learning is an art of studying algorithm that learn from example and experiences. Deep learning. So, deep learning is a subfield of machine learning. So this does not mean the machine learns more in depth knowledge. It uses different layers to learn from the data. The depth of the model is represented by the numbers of layer in the model. Then you have an expert system. So this expert system is an interactive, reliable computer-based system. Okay. So and fuzzy logic. Now all of you are aware about the application of fuzzy logic. We have gone beyond them. Okay. So that is one aspect. Then neural network. So it is like, what is neural network? It is a computing system made up of a number of simple or highly interconnected processing elements, which processes the information by their dynamic state responses to external units. So this thing you have studied, it is more related to this, but how it is applied in our problems, in our solutions. Okay. So in our problems, in our solution, it is like a basic unit of computation in neural network is neuron, and often is called as a node or a unit. So it receives input from a small other node or from the external source and computes an output. So there are multiple uh, multiple neurons. So in our case, let's say there are temperatures, there are levels. So there are a lot of datas which are coming. So you have to, and you have to develop a network. Let's say I have a current data, I have a vibration data, I have a temperature data, I have a frame size. And based on that, those datas are coming there. Some pre-trained network is there. So if I want to predict the health of the motor, or if I want to predict any abnormality in the motor, then I can predict with this different real-time data. I compare with already stored data. Like in cloud, I have an algorithm where multiple data's inputs are there, and based on that input, your motor health is predicted. Now, the major solution is FFT based solution to predict the motor health. So real-time FFT, fast Fourier transform takes place and it predicts the health. So if a vibration data, temperature data, current data, or intermittent temperature data, or even for the case we are feeding real-time 10 delta test with some sensors, like we are feeding insulation, we are checking the insulation health. So with that, you can predict even temperature rise. If the operation continues, the screen displays for next hour, this will be the inside temperature of the motor. So either you take corrective action or continue with the process. So that's how the in behind, like the backend neural network works when it comes to the check the health of the motor. Okay. So this all these things we are aware. Input nodes, which is an input layer, hidden loads, these are hidden layer, output nodes, then connection and weights. So these are where you give all the equations and all the previous datas. Then activation functions or final decision, which is taken where. Okay, learning rules. If this happened, then this. If that happened, then that corrective action. So this is just a basic idea, and why it is important when it comes to industry. Okay, we have talked like, say, like this, we have been talking since 1 hour. So it is like the main aspect is to take a real time decision, take real time accurate decisions. Okay. So where it is used, industrial application of machine learning, where actually it is used. So predictive maintenance. So there are a lot of research, lot of literature, but if you see the oldest paper on FFT analysis based motor health prediction. Now, basic concept is this only. You see, you search the paper, the very first paper which was published based on the FFT analysis, which will predict the health of the motor. And now, like since when you can check on the ABB website, so the main industry player is ABB. So ABB has provided this solution since like before 5 years, I think at least. Since like in plant we have discussed this thing, and like since 5 years they were approaching the industry. Now industry is expecting accepting this solution. So before 20-25 years the first paper was written based on this, and the first commercial product was realized before 5 years only. So that's how the process, or I don't know where the time is taking, why the solution takes so much of time. After creating a solution, the second most important step, let's say ABB, like I give the real time example. FFT based, lot of research papers are there. Let's say when ABB comes into a picture, ABB sees all those paper, ABB sees all those results, then they start developing the product. Once they develop the product, once they develop the solution, okay, it takes another 5-10 years. Then they come up this product with the in market. So in market they have to convince the business. A business is like this steel industry or a metal industry or a fertilizer industry or a pharma industry. So these industries are having those electrical equipment, so they have to buy the solution from the ABB. So unless and until ABB gets the business from this industry, it is difficult to progress on this technology. So that's how the interlink. Barabar. So that the research are there. Let's say condition monitoring. Everyone has heard about condition monitoring, real time condition monitoring, but the actual solution accepted by the industry, it takes a lot of time. Okay, so a lot of validations are there because investment is done by them. Here we are writing paper and we are convincing the researcher, but the main thing is we have to convince those who are paying. Okay, those who are giving, they who are generating the revenue. So that's where the application or the development of commercial solution takes time. Okay, so like in a lot of areas it has progressed and it is now like on a right track. Then pattern recognition. So if I give you an example in of my industry, then there are a lot of surface defect. So we manufacture steel. So on steel, I need there are a lot of quality checks. So the surface quality is a biggest concern of our customers. So to check on this, we have image processing based algorithm are employed, and they take continuous photograph or scan the surface and predict the quality of that particular coil or that particular batch. Then, of course, smart management. So it covers everything. So industrial applications of a machine learning in all this predictive maintenance, condition monitoring, process optimization, inventory planning, pattern recognizing, even root cause analysis. So like boat eye or a fish burner, everywhere they are all now autonomous. Okay. So we have electric arc furnace. So in this, like I'll not go into much detail on this. Okay, so we are about to complete. So electric arc furnace is basically convert your DRI, that is a hot metal, into steel. So generally we melt. So melting happens. So melting occurs at certain temperature. So once you start with say 800 degrees Celsius to 1600 degrees Celsius, so we have to reach the 1600 °C. So to here the main thing is the temperature prediction, and at the same time electrical energy utilized in steel plant. So with the digital twin I get the real time information, or with the data I can predict that if I continue with this heat, then it will result into this much of loss. So continuous real-time data I'll get. So I'll just keep this part, and like I'll just give you this aspect. Then we'll cover the digital twin. That thing is still remaining. So what are the smart factories? So what is smart factory? The first is like sensor captures, AI ingest and apply intelligence to it. Third part is your platform sends command back to the process. So what is that? So first is there are communication takes place between sensors and those cloud on cloud computing. Okay, and computing takes place. So what are the result? You can expect high yield, quality boost, less unplanned downtime. So machine learning and deep learning are used to imagine this smart factory. So these are the case study. Okay. Uh, Again, it is related to motors, which we have already discussed about FFT analysis. So last part, let us quickly go through this, the digital twin. So it is a buzzword. Most of these industries, they are adopting this solution, which is a digital twin. It is basically combination of a SCADA and a cyber physical system, or much more advanced SCADA. So digital twins are virtual models of a physical assets or a system. Those are continuously updated with real-time data. In general, digital twin replicates the real world object or a process in a software and integrate live sensor data to mirror its behavior and the status. So it is like a virtual model that span asset life cycle 100%, like using 100% data transfer, using sensor input and simulate operations and monitor performance. That is very important. So main component of this are your real machine or a process is a virtual model, that is your digital replica, and a data link, that is communication layer and information sharing. So digital twins basically bridges physical asset and a digital model. So sensor networks feeds the live data into virtual model. This is very important. Already one motor model is there. Already one transformer model is there, or whichever plant model is already virtual model is already prepared. And in that virtual prepared model, some live data is fed, and what if analysis takes place with digital twin. What if means this is only like autonomous decision making, predictive mechanism, all this. What if, what will happen if this goes beyond this, what if this shut down, what if this value goes beyond this limit, what if the temperature goes is, what if the level goes down. So all these analysis are done real time, and it gives you the indication when to take correct decision. So this is digital twin, like a virtual representation of your factories, as simple as that. That is what the digital twin, not just a representation. At the same time, it will give you the corrective actions if something going bad or something going wrong. Or one KPI is that energy efficiency. Let's say I want to make this process energy efficient. So to have that energy efficient process, it will give me the real time indication. You take this step, you take this step, you take that step. So with that, you achieve the energy efficiency in that particular process. Okay. So it will predict the performance, it will detect the error, it will help the decision making. Then digital twin uses machine learning algorithm and process large quantity of sensor data. So there is a huge capability or with the like the capability of data servers with this digital twin is that they have a highest speed of communication. Then remote monitoring, preventive maintenance, and interoperability. So digital twin technology is used different enterprises, different applications. Some of the applications you will have CAD or PLM or ART or SA. It integrate everything as from asset to shop floor. It covers everything. Okay. So these are the advantages, and for this, let's say use case while using your digital twin, that is predictive maintenance. So AI detects a pattern indicating wear or failure in motor, bearings, or pumps. Digital twin uses this data to alert the engineers before failure occurs. So that is one part which is predictive maintenance. Process optimization. So AI models analyze process parameters. Let's say in my case, it is rolling mills, furnace, or a converters. So it suggests optimized temperature, pressure, and speed setting for higher yield, yani higher production and lower waste. So for each and every different process, let's say you have fertilizer plant. So there are some processes there. So to optimize this process, you can have the digital twin. Then quality prediction. So AI trained on historical quality data detects early sign of product defects like cracks. Like it is like in my case, some rolling process is going on. So to predict the quality of the product, I need a rolling parameter. So with every engineering process, there are engineering parameter. So if that product quality is compromised, or the quality of if not up to that mark, then in that process the variables are changing. So current, in our case, let's say current voltage or the speed or the temperature. So all these process parameters are very, very important, which ultimately decides the quality of that product out of that process. So if the product quality goes down, it is because of the variance in those parameters. So straight away, you have models already pre-trained network in which that if this quality results, then these are the process parameter. If this quality, like the variation in the quality, it comes because the process parameter like this. So there are multiple data are there. Based on that, you predicted the bad quality. You have real-time data of earlier. You have historical data. So based on that heuristic approach, you can compare the real-time data. So this is how you can predict the quality and you can control the process parameter. Then you have autonomous decision making. So in advanced plant, AI agents within digital twin automate and routine decisions like load balancing or maintenance scheduling. So maintenance nowadays, maintenance scheduling, which will consider all aspects, are the decisions which are taken based on the digital twin or programs. So one era came which was Excel sheet. Now Excel sheet is still automated, and it is the data of Excel sheet is fed into some software or AI based software, and they give the final output. Okay. So these are the basically use case example I've just done. This is like a graphics of a digital twin. So here on left side is an actual plant, is a real time. Then on right side, you can see the digital twin. So component, equipment, combining both this, you have a whole plant, which is like a line or a workshop or a factory. So if we define a common construct, this is data, models, and service API. So application programming interface, that is API for digital twins. So API is like, it is like a service or a software service. So we can build these digital twins for component, and from them we can construct a digital twin for a equipment or a production lines or a workshops or a factories or even enterprises, just like we construct these entities in real world. So digital twin thus offers a systematic approach to represent complex real world system, including those in manufacturing environment and a digital space. So this will build a comprehensive digital factories. So ultimately data goes both ways. Like from real twin, data goes to digital twin, and from digital twins, the command goes to the real twin. So person sitting here can take the autonomous decision. Okay. So from data to commands, decisions are real time in with the software or the programs written in some algorithm. Okay. So that's how the smart factories and digital twins are realized. Okay. And this is what the data science cycle, this is how this data transfer takes place, and the data science is realizing. First is the business understanding, that is ask the real time questions, define objective for the problem that needs to be tracked, data mining, that is gather and scrap the data necessary for the project, then data cleaning, na, the multiple second by second level, temperature, pressure, all those process parameters are coming. I have to check whether it is okay or not. I have to clean the data at that moment only. Then data exploration. So from hypothesis about your defined problem, let's say motor health. So current temperature, vibration, and other bearing health data based on that, some hypotheses are there, and I will analyze the data. Then future feature engineering, feature extraction that we have seen in last session also. So select important features and construct more meaningful ones using the raw data that you have. बराबर. Then predictive modeling. So train machine learning models, evaluate their performance and use them to make prediction. Then finally your data visualization. So communicate the finding with key stakeholders using plots and interactive visualization. So here, if from the industry perspective, an operator sitting in a control room, he visualizes a SCADA screen and a digital twin differently. A manager above him sees something on SCADA screen differently, and a plant head sitting inside his cabin, observing all these data points, his intention is different. But from to satisfy both, like all these three aspect is like from a simple AI machine learning based data science solution. You can satisfy all these stakeholders by just one solution. So that is what a capability from the industrial perspective. Okay. So that's it from my end. So here, like this is just an intro. There are a lot of technological things are there to realize this thing, starting from a database or database system to management to the final applications. Okay, so PLC and SCADA is now just a basic things. To have AI or machine learning, you need a strong domain knowledge as well as the mathematical programming knowledge. So this is not just a software thing. Your students needs to have a both approach, a software modeling as well as the fundamental aspects of your automation or a motor or a transformer or any engineering electrical related process. So here you can realize you can give a complete solution if you know the know-how of both these aspects, and that where the actual scale is demanding. If we are asking for a skill, then fundamental is compulsory. Above it, they need to develop these skills which will be accepted by the industries, and ultimately they will help to the business or industry. Okay, so that's it from my side, and I'm open for question. Ask question in a chat box probably. I think okay. So already there are a couple of questions. So somebody has written, which software you use to create a virtual model for a digital twin in electrical engineering. See, again, it is like electrical engineering is a very in general. So here the things now has come on the application aspect, whether this twin solution is for some power plant, this solution is for some steel plant. Okay, so based on the application and the industry where it is the software used. So there are a lot of OEMs. So Siemens has its own solution, ABB has its own solution. So all this industrial software solution provider companies individually provide this thing. And in this, if we want to have this like as a solution, as an customized solution, then of course nowadays slowly MATLAB is also having this kind of capability. Okay, so how to, like, other question is, let me go through again, sorry. How do digital twin improve a power distribution system? So power distribution, as I told you, there are a lot of aspect of power distribution. Let's say if you are nowadays there are in distribution also some we have renewable energy. So renewable energy grid where one distribution pole is there. So if you want to have a power quality on that DP where there are multiple renewable sources are connected. So on that it and from that DP or distribution pole, you are feeding a lot of non-linear load. So real-time power quality analysis you can do using digital twin. You can model on that network. Okay, any other question?
Okay, I think there is no more question. Again? Okay, okay. So thank you very much, Chinmay sir, for a wonderful session. It was very informative, and I believe that uh, people have gained lots of output from this session. Thank you very much.
Okay, thank you. Thank you.